of view, but I would expect that there will be actually, in general, two draws to potentially make. You have to make the draw to see where you're thinking of going, and that'll have a certain cost. And then if it's a downhill move, you have to make another uniform draw to decide whether to accept it or not. Uniform draws are quite cheap. Gaussian draws these days are quite cheap as well. But you're right. If you were to decompose the actual computational cost of the algorithm, most of it's coming from making the random draws, because this calculation is quite cheap, and yeah, the ratio is cheap, and making this assignment is cheap as well. So you're right, most of it's in the generation of the random deviates. Well, you just have to evaluate an analytic function that has an analytical expression at a particular point. And so notice what happened here when we look at this ratio. The acceptance probability depends only on the ratio of the target density where you're thinking of going to where you are now. And remember, we agreed that that would mean it's not necessary to use a normalized version of the target density. So we can use an unnormalized version, which is of the type we would have typically if we didn't bother to evaluate the normalizing constant. We'll just have an analytic expression for the prior and an analytic expression for the likelihood multiplied together. And without having to evaluate the normalizing constant, we can stick that in right here and that right here, and the normalizing constant would have canceled anyway. So, desirable criterion 4 of the 4 things that Metropolis was interested in getting is satisfied by everything being driven by the ratio of these two densities at 2 different points, and the same density at 2 different points, which makes the constant cancel. And the other things are also automatically specified or automatically achieved. The set of possible values for the draws in the Markov chain is automatically set up to be the same as the set of values in the target if you set the Markov chain up correctly. It has to be easy to sample from, and Gaussians and uniforms are really easy to sample from. And most importantly, this is the part that this sketch here has not shown is true. It turns out that with those 3 particular rules for how to behave, you have created a nice Markov chain that does have an equilibrium distribution, and the equilibrium distribution it has is the target. That's the really amazing part. And a bit later in the organized notes, I've provided a sketch of the proof of that for people who are interested in looking at that. Chris Barker has forwarded me a link, which I will put on the web page. MCMC is great for small and medium-sized data sets, but it can be overwhelmed computationally by large data sets because it doesn't scale well in the number of rows in your actual data set. And so people have been, including myself, have been developing methods recently for making approximate Bayesian computations. And so ABC is the hot acronym these days about approximate Bayesian computation. And the section on Bayesian statistical science of the American Statistical Association is holding a webinar next Thursday, a week from yesterday, out here it would be between 9 a.m. and 11 a.m. because that's noon to 2 Eastern time. And it doesn't cost very much. So if you're a member of this section, it's $60. If you're an ASA member, it's $75. If you're a non-member, it's $95. And in addition to hearing the guy talk, he's a guy at Duke. I'm not sure how big an expert he is on ABC, but I bet it's going to be good. And in addition to hearing him talk, you'll get a copy of the slides that he's talking from as well, and all the code and so on that he's using. I myself am probably going to register for this and try to take some of these ideas to the later part of the course. I was going to do it on the basis of some journal articles, but if this guy can help us all provide us with some easy to understand simple examples, then the more the better. So I'll put this link on the course webpage. I might not get to it until Sunday morning, so you could copy it down if you want now. www.amstat.org gets you to the ASA /section/SPSS statistical section on Bayesian statistical science /webinar.cfm gets you to all the latest webinars, and this is the very latest one, so that's the one that's on the list. So, so I hope that's useful to you. And returning to the notes, what I'm going to show you on this first page is, first I'll just tell you what the, I'll show you the, I'm being inarticulate. Let me start that sentence over. So Metropolis came first in the 1940s with this algorithm I just showed you. Then in the late 1960s, published in 1970, along came this guy Hastings, and Hastings discovered a potentially useful generalization of the Metropolis algorithm that is based on the following observation. And I should have said this as a criterion to make this picture work. This version of the algorithm only works if the proposal distribution is symmetric, is a symmetric density. So has to be symmetric. And the normal curves centered at where you are now satisfy that, of course, and the uniform distribution that's arranged symmetrically around where you are now. You could think of lots of distributions that would all work. So Hastings said to himself, well, I bet I could get extra Monte Carlo efficiency sometimes if I worked with proposal distributions that were not symmetric. In particular, suppose that the target lived only on the positive part of the real line and actually stopped right there. Once the proposal distribution had moved down into this corner, it would start making proposals into a region that's impossible, and so you'd have to reject those proposals, and so that would lose some Monte Carlo efficiency. So if you could have a proposal distribution that only lived on the positive part of the real line for a target that only lived on the positive part of the real line, that would be a good thing. And so Hastings said to himself, how can I generalize the Metropolis story to work with proposal distributions that aren't symmetric? And it turns out that it involves just a small change to the Metropolis algorithm as follows. So let's let theta t stand for where you are now, and theta star for, oh yes, thank you. And let's let theta star stand for where you're thinking of going. It turns out, as I was saying before lunch, that there's an enormous flexibility in the choice of the proposal distribution, which I'm going to call lowercase g of theta star given theta t, namely what's the probability that you would move to theta star given where you are now. And the answer turns out to be that you have even more flexibility than in ordinary rejection sampling. So I mentioned to you just a second ago that the original Metropolis idea was to work with symmetric proposal distributions in the sense that you see there in this area that I'm highlighting now with the mouse, namely that the density has the same value if you interchange the role of theta star and theta t. That's the sense in which it's symmetric, and you can see that the normal distribution centered where we are now would have that role. But Hastings pointed out that this could easily be generalized, and now we have what people call the Metropolis-Hastings algorithm, or MH for short. And Hastings showed that you'll get the correct stationary distribution for your Markov chain by making the following choice for the acceptance probability. Now, this is a fancy way to write things, but the idea of min of something with 1 and something else simply says, if the ratio to the right of the 1 comes out bigger than 1, then you accept with probability 1. So you accept with the smaller of those two numbers. You can see that if we were to take the proposal distribution and make it symmetric, the part in the numerator that involves itself a denominator, g of theta star given theta t and y, would cancel with the other g in the bottom part, and we get back the Metropolis acceptance probability. So it turned out Hastings was able to show that a simple story in which you're making a ratio of ratios involving comparing the height of the proposal to the height of the target will allow you to use asymmetric proposal distributions as well. And that expression 14, that ratio of ratios, is interesting because if you look at it, it's the same as the ratio of two von Neumann ratios, because you remember they were the form P divided by capital G. You evaluate the height of the target versus the height of the envelope function. But you remember also that the envelope function was not normalized, And whatever normalizing constant you would use would have canceled in this expression here, because you could have used capital G or lowercase g in this expression and you get the same thing. So actually what Hastings found, interestingly, is that the right thing to do is to use an acceptance probability that is governed by a ratio of two von Neumann-like ratios from ordinary rejection sampling. And it turns out that the proposal distribution, g of theta star given theta t, can be virtually anything, and you will get the right equilibrium distribution. There's almost no restrictions on it. So here's a little box that summarizes the Metropolis-Hastings algorithm. To construct a Markov chain whose equilibrium distribution is p of theta given y, choose a proposal distribution, g of theta star given theta t and y, define the acceptance probability by that ratio of von Neumann ratios a minute ago, and now we have 2, 4, 6, 7, 8 lines of code again. But the code is different than von Neumann, so let's look at it. It starts the same, so you initialize the chain somewhere, theta 0, and you set your counter for iterations to 0, and now we repeat over and over again until we've achieved as many draws as we like. So first we sample theta star from the proposal distribution, given where we are now, theta t. Then we sample a uniform draw, and if the uniform draw is less than or equal to the Metropolis-Hastings acceptance probability, then we have a then versus else. If that's true, then we move to the new place, theta star, otherwise we stay where we are and increment the counter. And now keep doing that for as long as you like, right through the burn-in period, right through the monitoring period. And as we just noted, when the proposal distribution is symmetric, you get back the ordinary Metropolis acceptance ratio. So here's going to be an example of Metropolis-Hastings in action. We talked about the NB10 data. We were using Gaussian models for it, even though it didn't have an actual Gaussian form, and we'll improve on that this afternoon. Suppose you were working with a Gaussian model where you knew what the mean was, but you didn't know what the variance was. Then you can write out the likelihood function, and this is a lot like one of the homework problems, one of the problem set problems I think it was from problem set 3. The likelihood function looks like equation 16, which after you finish simplifying it a bit, comes out to look like, as a density in sigma squared, it behaves like sigma squared to the minus n over 2, e to the minus stuff over 2 sigma squared. And that's actually recognizable as a member of the inverse gamma family. In fact, it's a member of that thing that earlier we called the scaled inverse chi-square family. And all that means is that this is a rescaled version of the inverse gamma function family, which in turn is arrived at by taking draws from a gamma distribution and taking the reciprocal of those draws. So it's all kind of well-known distributions. But the scaled inverse chi-square family with parameters nu and s squared, when used as a prior, for example, is interpreted as having s squared, your current estimate of sigma squared, based upon new observations. So it acts like a prior sample size of nu, and then in the posterior, that would be a posterior sample size of nu. And in fact, this is yet another one of those lovely families where the product of two such densities is another such density. And so it turns out right away that that is the conjugate prior in this version of the Gaussian model where you don't know what the variance is, but you do know what the mean is. And so having done that, the posterior distribution looks like that. And so it's yet another member of the scaled inverse chi-square family. And the updating rule makes good sense. The prior sample size nu updates to nu plus n, the total data sample size of prior information plus data information. And the prior estimate of s squared, namely of sigma squared, namely the s squared you put in the prior, gets updated to a weighted average of the s squared from the prior and the sample variance, where the prior gets nu votes in the weighted average and the data estimate gets n votes. So it's just exactly what you would have expected involving a weighted average of the two information sources. So that solves the posterior problem. And if you could figure out how to sample from that, you'd be done. And it wouldn't be very hard using the functions in R, because that's a member of the inverse gamma family. So you just sample from the relevant gamma and take the reciprocal, and you have draws from this distribution. So that works great. But suppose you wanted, for practice, you wanted to work out a Metropolis sampler for working with this, or better, a Metropolis Hastings sampler for working with this, then let's see how it would go. So your main choice as a user of the algorithm, and this is a choice that you won't have to make when you use software like Winbugs and the other routines that are out there for helping you with this. The really hard part of Metropolis is working out what the proposal distribution is to get a decent Monte Carlo accuracy efficiency, and all these packages make choices for you. And in fact, if you had to do it yourself from scratch, it's no fun. So it's good that we have these packages that do it automatically for us. But let me just show you the logic quickly so that you can see what would be involved if you tried to do it for yourself. So I have to pick the proposal distribution, PD for short, and it has to be a function of sigma squared given where I am now. And you saw that requirement that a Markov chain be nice in terms of that concept called irreducibility. It was an idea that you wanted to make sure that the chain, I used the verb to mix, you want the chain to mix well. It should move freely and fluidly around all the different possible values that it's trying to sample from. A chain that does that, we agree to say a chain that does that mixes well, and one that doesn't do that mixes poorly. And so we would like to find a proposal distribution that guarantees good mixing. And I'm afraid the truth about it is that no one has come up with a surefire strategy for always succeeding at this task. There's still a little bit of art along with the science in constructing proposal distributions. But there are a couple basic ideas that often tend to promote good mixing, and here they are. The first idea is to try to pick a proposal distribution that looks like a somewhat over-dispersed version of the posterior you're trying to sample from. And so if the posterior is Gaussian, you can use a Gaussian with a bigger standard deviation as an example of a good proposal distribution, and so on. And of course, that's circular, right? Because if you knew what the posterior was, then you would already know what the posterior is rather than trying to have to come up with an over-dispersed version of it for the purpose of sampling from it. But that's okay. That's still actually kind of a useful idea. And then the second one is to try to set up the proposal distribution so that the expected value of where you're going to move to next, given that you accept a move away from where you are now, is to stay where you are now on average. In other words, you expect to stay where you are, and that means that you'll be forced sometimes to move to the left of where you are and sometimes to the right of where you are, and that'll create good mixing. For people who know about theoretical probability, that means that you want to create a martingale so that it's a stochastic process. It has the property that it is, in expectation, it stays where it is, but of course it's moving all the time, but it expects to stay where it is. And so that way, when you do make a move, there'll be an approximate left-right balance in the direction that you move, and so you can hope that will encourage rapid exploration of the whole space. So using idea 1 above, a decent choice for the proposal distribution in this Gaussian model with unknown variance might well be some other member of the scaled inverse chi-square family. So I'm going to try to sample as my proposal from the scaled inverse chi-square family in order to learn about the scaled inverse chi-square distribution that is the actual posterior. And this distribution turns out to have mean given by nu star over nu star minus 2 times the variance sigma star squared, as long as you have at least 2 degrees of freedom. And to use the second idea, then, I can choose any nu star greater than 2, and as long as I take sigma star squared to be equal to that mean for centered at where I am now, that will force the proposal distribution to be centered at where I am now. So that's a little equation that I can use to cut down on the range of possible specifications that I might use. And so I'm going to use this member of the scale inverse chi-square family with nu star degrees of freedom, and that as its current estimate of the variance parameter, nu star minus 2 over nu star times sigma squared t. And that leaves this number nu star as a kind of tuning constant. And it's analogous to, back here in this picture, it's analogous to having the proposal distribution standard deviation act like a tuning constant. And I'm about to show you in a little while that in a setting like this, where you're using a Gaussian proposal distribution, if you choose the proposal distribution standard deviation to be too small, that gives you one kind of mistaken, not optimal behavior from the Markov chain. And if you choose it to be too big, that gives you a different kind of non-optimal behavior. So it's kind of like Goldilocks and the 3 bears. The porridge too cold, porridge too hot, porridge just right. There's going to be an optimal value for the proposal distribution standard deviation in the middle between those two extremes. And I'll say more about that later. The same idea with this number nu star. If we make it too small, it'll make one kind of mistake in terms of Monte Carlo efficiency. If we make it too big, it'll make a different kind of mistake. So this picture here shows two limiting cases of the output from a Metropolis Hastings sampler. That would be the top and the bottom two pictures here. And the third picture in the middle I'll talk about in a minute. The top picture looks like the skyline of a city you've never seen before. And it's an example of a kind of output from a Metropolis Hastings sampler that I would call blocky, because you see what's happened is that the chain has taken literally that third part of the algorithm, and it has literally stayed in the same place across many iterations before jumping somewhere else and staying there for a good long while. So what's happening here, you can think it through. Let's look at this. Why would you stay where you are now? Because you're trying to move to some place that's a move downhill, and you fail to move there. So how do you get to have downhill moves from a place like this? It's because your proposal distribution standard deviation is too big, because you're proposing really ridiculous moves way out into the tails. So when you get blocky output like this, it tells you that your proposal distribution standard deviation or some other measure of scale for it is too big. At the other extreme, what if your proposal distribution standard deviation is too small? Then you would end up accepting nearly all the proposed moves, but because each move that you actually agree to make is so tiny, you'll move very slowly around in the parameter space because you aren't actually being bold enough to suggest relatively large moves. It's like rock and a hard place or Scylla and Charybdis or something. The upper panel there is one kind of mistake, the blocky output. The bottom panel is a kind of output, it's a different kind of mistake that I call sticky. So you can see that the chain, each time it moves, it's hardly moving anywhere at all. And so that corresponds to a situation where we do have a high acceptance rate, but it's actually too high because we are not being as adventurous as we could be in moving around more. So the bottom panel of the three corresponds to an acceptance rate that's too high. The top panel corresponds to an acceptance rate that's too low. And there ought to be some sweet spot in the middle, and people have done some theoretical work to work out what the optimal is. The optimal for a single parameter in the Metropolis Hastings world turns out to be about 44% acceptance rate. And where that comes from is why that's the right number. It's hard for me to motivate for you. But I've plotted in the middle panel the output of using this scaled inverse chi-square proposal distribution at the 44% acceptance rate. And you can see that it achieves a nice compromise between the rock and the hard place. It does have a few places where it's behaving in a blocky fashion, but it also moves around quite a bit and avoids being too sticky as well. So these are time series traces of some typical output of the sampler with that nu star tuning constant ranging from 2.5 to 20 to 500. And those acceptance probabilities correspond to only 7% when nu star is small, all the way up to 86% when it's large, and there's the magic number 44% in the middle when it's in the middle. And so I've already said pretty much what's going on in this last paragraph. When the proposal distribution SD is too small, which corresponds to small values of nu star, the algorithm tries to make big jumps around the theta space, which is good because if you can move to there, you really explored the space well. But it's actually trying to make jumps that are too big, and so most of them get rejected. So that's bad. At the other extreme, with large nu star, which corresponds to large proposal distribution standard deviation, oh no, the other way around. They have an inverse relationship. When the PDSD is too small, that corresponds to a large value of nu star. Then the algorithm accepts almost all of its moves, but it takes a long time to fully explore the space, and that's not good. And so right in between, the nice porridge just right turns out to be the 44% acceptance rate for one-dimensional unknowns. Pardon? Uh-huh. That's correct. Uh-huh. Yeah, it's doing okay on the ranges, but you can see, I hope you can see that it takes a very long time to get from the high end of the sigma squared down to the low end of the sigma squared. Pick a part of the output where it's at near the high end of sigma squared and look at how long it takes to get to the low end from there. It takes a long time. Whereas the one in the middle is, you see there's a number of moves where it fluidly moves right away from a very high value to a very low one. So it's doing a better job of quickly exploring the space. You're right. All three of them amazingly get the range correct. And isn't it amazing, if you take that blocky output, what you're literally being asked to do in your mind is to take the blocky output and turn the whole thing on its side and let all those values dump down into a little data set and draw a histogram of them. It is the correct distribution. It actually, this business of staying where you are for all those different periods turns out to be exactly the right thing to do. It's just astonishing that that's the right thing to do, but it turns out to work. So there's your 44% optimal thing, and I've shown you that the central panel does the right thing. Even with this optimization, you can see I'm not claiming this is the best possible Metropolis Hastings sampler. I'm just saying it's the best possible Metropolis Hastings sampler with a scaled inverse chi-square proposal, and that particular form of the other way I chose the parameter with that martingale idea for the other parameter. So this is the sort of thing that people who are writing packages to allow other people to use MCMC in a relatively user-friendly way, this is the sort of thing that we, the developers of such software, worry about. You as a user don't have to worry about this stuff in practice because someone else will have already chosen the proposal distribution for you. Now, as I mentioned before, the mixing is not wonderful for even the best one of these things, but we're going to go ahead and overcome that by simply using the fact that we have fast computation speeds these days and just take a large number of draws and get it done that way. Everything I've done so far makes it look as though the algorithm might only work for a parameter vector that has dimension 1, but actually it's pretty interesting. If you look back at the algorithm, there's nothing in the algorithm that assumes that theta is a scalar rather than a vector. And it turns out to work equally well for theta as any vector of finite length, because P of theta given y is just a posterior distribution in k dimensions. The proposal distribution is just a distribution in k dimensions. The acceptance probability is just a number. And now you go ahead and do everything that it says to do. So it works equally well for vector unknowns as it does for scalar ones. Thank God, because otherwise, if you can only do it one thing at a time, that wouldn't be a very useful algorithm. And in fact, when the vector of unknowns is really a vector, there's actually quite a lot of even more freedom on your part than there would be when there's only a single scalar. I've already mentioned this fact at the bottom of page 34, that you don't have to work with the normalized version of the density because whatever you put in front of that would cancel in the ratio anyway. Now, there's even more flexibility in this algorithm than might first appear because you can accelerate the Monte Carlo accuracy in many cases by identifying a set of what are called auxiliary variables to be sampled along with the unknown parameters you're interested in. And these variables are called latent variables often because the word latent means that they're unobserved, but it's interesting to think about what their values would be if you could observe them. And ironically, it sounds like a funny idea, but if you only have 3 parameters in your model, for example, and you can find 10 auxiliary variables, it sounds as though that would sampling all 13 of those things would have to be much slower than working with the 3 by themselves. But in fact, if you choose the 10 auxiliary variables well, the gain in Monte Carlo accuracy can overwhelm the loss in speed of having to work with 13 of the variables at a time. And so there's a whole range of clever ideas that people have invented trying to figure out how to bring in these latent variables and make things go faster and get better mixing. So if I start with the original set of unknowns theta and I add to it a block of latent variables or auxiliary variables A, there turns out to be even additional flexibility in the Metropolis Hastings algorithm. You can update all of them at once, or it turns out with appropriate modifications of the acceptance probability, you can divide that entire theta comma A vector up into components and update the components one at a time, including taking each element of theta and updating it one at a time. And people call this single component metropolis Hastings sampling. What you do is you have k different proposal distributions, one for each of the components. And there's a very nasty, I won't even read this out loud, I have to invent very nasty notation to show you how to do it. But when you're done, you end up with the correct acceptance probability to have this unpleasant form that you see in equation 19. Now, something interesting is as follows. When you have a distribution like the one that you see for P right there, look in 19, it says P of lambda I star given lambda T minus I, comma Y. The part that goes, forget about the T part and just concentrate on the part that says P of lambda I given lambda minus I. Remember we had this notation that means lambda minus I means all of the lambda vector except with component I omitted. These things have a special name in the history of this sort of work. They're called the full conditional distributions for a particular multivariate probability distribution. And let me give you an example of what I mean. We're about to fit, in order to get a better answer for what's going on in the NB10 data, we're about to fit a model that was impossible to fit using conjugate priors, because there aren't any. A model in which we're going to say, if you knew what three parameters were, mu and sigma squared and nu, the yi's would be like IID draws from a t distribution with new degrees of freedom and location parameter mu and scale parameter sigma or sigma squared. And then we have to be able to put a prior on mu and nu and sigma squared, so it's going to have some prior. Sigma squared and nu. And that's going to be our sampling model for the NB10 data as I runs from 1 to n, which was 100 in that example. So theta, the vector of unknowns here, contains mu and sigma squared and nu. And so now let's get into this full conditional idea. There's going to be three of them. The full posterior distribution, first of all, for this would involve a three-dimensional distribution that goes mu and sigma squared and nu, given the data vector and the background information. That's a three-dimensional distribution. It's going to be hard to visualize. It's going to be hard to think about. That's the complete posterior distribution. But what if I could talk to you about the marginal distribution for mu if you knew what sigma squared was, and if you knew what y was, and if you knew what the data was, and if you also knew what the background information is? Do you think that would be easier to think about than the entire complete posterior distribution? The complete posterior is a posterior on three unknowns, and all you have to condition on is the data. Check out this new thing, which is called the full conditional for mu. So that one's there, the full cond for short for mu. Wouldn't it be easier to learn about mu in a model with parameters mu and sigma squared and nu if you already knew what sigma squared and nu were? Wouldn't it intuitively be easier to learn about mu? So the idea behind the full conditional is you temporarily pretend that you know something that you don't know in order to learn more about the other thing that you're really wondering about. That's the full conditional for mu. The full conditional for sigma squared looks similar, except you permute the ingredients. So this is the conditional posterior for sigma squared given mu and nu and y in the background. And I have to scroll up because I'm down too low. That's the full conditional for sigma squared, and it has the same sort of logic. Wouldn't it be easier to learn about sigma squared if you knew what the other two parameters were? And then finally, the third one goes nu given mu and sigma squared, of course, and y in background. That's going to be the full conditional for nu. Now, it's a remarkable thing about multidimensional probability distributions that they are completely characterized by their set of full conditionals. In the following sense, if I told you all three of these distributions, then that would imply one and only one joint distribution. And the other way around, if I told you the joint distribution, that joint distribution implies one and only one full conditional for each of the three components. So it's an interesting fact about any joint distribution that it is completely and uniquely characterized by its set of full conditional distributions. So it's a little bit like, again, that old story about the blind men and the elephant that I think I mentioned briefly in passing in one of our earlier visits, where one guy feels the trunk and another guy feels the leg and another one feels the tail and so on. These things act like the trunk and the leg and the tail, but unlike the blind men and the elephant, if you have all the full conditionals, you can completely characterize the whole elephant. You get the whole elephant. And notice what happens in this expression in equation 19 here. The GI in this expression are the proposal distributions. If I chose the GIs to be the full conditionals, then what would happen is that all the stuff in that fraction right there would cancel and it would all come out to be 1. So if I choose the GIs to be the full conditionals, then the P's and the G's all cancel each other and we get an acceptance rate of 1. And that's kind of cool because that says that's a way of creating a Metropolis-Hastings sampler that always accepts every move that's proposed. And that sounds like it would be a very efficient way to do Metropolis-Hastings sampling because you would never be rejecting any moves. You'd always be accepting every proposed move. There wouldn't be any of this business of staying where you are now. You would always move somewhere new. This special case of Metropolis-Hastings sampling, where you choose the proposal distributions to be the full conditionals, is the version that those Gehman and Gehman brothers independently rediscovered. And they called it Gibbs sampling, although they didn't know at the time that it was just a special case of Metropolis-Hastings. So this is Gibbs sampling. And even though it's just a version of Metropolis-Hastings sampling, it's important enough to merit a summary of its own. The simplest way to use it, the most frequent way to use it, is with no auxiliary variables and updating each element one at a time. And so I will now show you on the pages over here exactly how you would use Gibbs sampling in the NV10 model. And then I'll show you the general statement of how Gibbs sampling works. So I'm trying to fill in the MCMC data set, and it's going to have a column for mu and a column for sigma squared and a column for nu. And later on, it's also going to have other columns as well for quantities that are based upon those three things. But for now, let's just think of it as having those columns. And I'm going to start off at iteration 0 at some values. So this is mu 0, sigma squared 0, and nu 0. And now I want to know how I generate a value right there. And the answer is I make a draw from the full conditional for mu, and the rule in Gibbs sampling is always to condition on the most recent value of all the other parameters. So here that would be make a draw from mu given sigma 0 squared and nu 0, and the data and the background. That will give me something I'll call mu 1 star. So the rule, as I'm writing down here, is always use the most recent values of the other parameters. And so the way that plays out here is now I'm trying to figure out how I fill in that number there. And the answer is what you do is you draw from the full conditional for sigma squared. But now, instead of going back up to the previous row to get your value of mu, you use the value you just got. And so this becomes mu 1 star. And now the most recent value of nu is still the row in the value in the previous row. So you use nu 0 there and y and b. And that'll give you a number I'm going to call sigma squared 1, the whole thing star, let's say. And now finally I want to ask myself, what do I do right there? And the answer is draw from the full conditional for nu, always using the most recent values of all the other parameters, and they happen to be the ones in the same row right here. So I use this time mu 1 star, sigma 1 squared star, and the data and the background. And having filled in all three of those numbers, now I have this thing called new one star. I've just described the algorithm to you because now we know how to fill in every row, every element of every row, and now go back and do it again. And so the algorithm never uses information any farther back in time than the previous row. That makes it Markovian, right? And sometimes when you get to the end of a row, it doesn't even look into the back row at all. It just uses the stuff in the same row. Are things better now? It sounds like they might be better. And that's a dead battery. And this one we believe is still alive.
So,
Yes, please.
this, you told us the rule that you always have to use the first value.
Right. It follows directly from 19 that you always accept every move because the proposal distribution is the same as the full conditional. And if you look at that, the full conditional for the next observation cancels against the other ones in the numerator and denominator, and you get out an acceptance probability of 1. No, that's correct. There will not necessarily be any advantage, but if you always use the rule that you condition on the most recent values of every single other parameter that's going into the full conditional, then it doesn't matter the order in which you do them. You'll always get the right answer. Yes, that's right. As long as you, that's true. As long as you, that will be slower, probably be less efficient, but as long as you use the rule of always using the latest values of all the previous variables, there you go. So here in equation 20 in the box is the algorithm for single element Gibbs sampling. So to construct a Markov chain whose equilibrium distribution is the posterior that you're interested in with theta as a vector of length k, you start somewhere. So you initialize the Markov chain at some elements theta 0, and you set the iteration counter to 0, and you just repeat. So first you sample from the full conditional for theta 1, using all the values for the other variables that you got from the previous row, and that gives you a new theta star for 1, whose element is now theta star t plus 1, or now 2. Then in the second row, you use the most recent value for the theta 1 column, and then all the old ones, and then you keep doing just what I said. Always use the most recent values, and out comes the Gibbs sampler. If you were to, well, let's see, returning again to the logic of this little diagram here, the only parameter that you need to use data from the row above 4 completely is the first one in your scan, as it's called. We're scanning from left to right. Oh. Okay, in other words, so you get your mu1 star from the previous row for the sigma and squared and the new. Then when you get to sigma squared, you mistakenly use the old mu0 and the old nu0, because you have to use the nu0, but use the old mu0. Then it won't be a legitimate, you won't converge to the correct stationary distribution. You've broken the basic rule of how to build a Markov chain that has the correct stationary distribution. It may well converge to something as a stationary distribution, but it won't be the target that you want. That was based upon, the target was derived by working out the full conditionals. So the rule you're breaking is always condition on the values of the parameters that are the most recent ones sampled. And that may sometimes involve looking back into the previous row, but will not always involve looking back into the previous row. You just always use the most recent value of the other parameters that you have to fill in as part of the full conditionals. Yes. You never look at the picture here. To fill in row 1, I never have to know anything in row -1. So I'm only conditioning on where I am now plus where I just was. And so that's Markovian. We never have to go back more than one period. It does work. So just as an example, you wouldn't have to do this yourself, but just an example of how to create full conditionals in case you ever needed them, you would think about them as follows. Here's the NB10 data. I was starting to say that we ought to be using a T-model for the data, and that's a simple way to write the T-model, the same one I wrote down on the handwritten notes a minute ago. I should tell you something interesting about the T distribution that you may or may not know, and then we'll get back to talking about the full conditionals. So the T distribution turns out, as long as the degrees of freedom are bigger than 2, the distribution has variance sigma squared times nu over nu minus 2. And that's a little bit of a difficulty for working with the T distribution, because that means that the shape of the distribution and the scale are mixed up with each other or confounded. If the variance of the distribution is supposed to be fixed at some value that corresponds to whatever the sample variance was, you could either arrive at that value, let's say that variance was big, you could either arrive at that value by having a large value of sigma squared and a large value of nu, or equivalently a small value of sigma squared and a small value of nu. Both of those things taken together would give you a large value for the variance. And so essentially that means that we're going to find a relatively high degree of correlation between the sigma squared parameter and the nu parameter in this model. Okay, but here's a better way to think about the T model, and it's a way that you may never have thought of before, because if you've been mostly reasoning probabilistically in the frequentist world, people just take for granted the T distribution as a distribution of the repeated sampling distribution of that thing that Mr. Gossett needed in order to work out the T machinery. So for frequentists, we tend to think of T distribution as the repeated sampling distribution of y bar minus mu over s over the square root of n when the data are drawn from yi given mu and sigma squared IID from normal mu sigma squared with both parameters unknown. So this is the frequentist way to think about the T distribution. But if instead you were thinking about the T distribution as a model for data, that would be one of the ways to think about it that comes up more naturally in the Bayesian way of looking at the world. So T model for data, by which I mean you're using the T curve as the sampling distribution. Well, here's what the T curve looks like. Here's the normal curve, and a T curve with a small number of degrees of freedom looks kind of like this. It's a little higher in the middle, and it has much heavier tails. So this one right here is normal, and this one right here is T nu, where nu is small. So how do you get a distribution that has heavier tails than the normal? Well, one way would be as follows. In the normal distribution, each yi is a draw from normal mu sigma squared. But in the T distribution with, in the T distribution with nu degrees of freedom, what if we tried to make the tail heavier by allowing each observation, while still having the same mu, to have its own variance? And that way, some of the observations would end up in the tails because they had bigger variances than the other ones. But if you tried to fit this model to data, of course, there's too many parameters, because now each observation, there's two numbers that you have to learn from each observation, not just two numbers overall to learn from the n observations. So we would have to do something hierarchical in which we would tell a story in how somehow all the sigma squareds are related to each other by being IID from some distribution. And it turns out that that mixture or hierarchical representation is exactly another way to think about how the T-curve is working. It's a model for data where you're using a measuring process that has the property that each time you measure that little block of metal, for example, it has all the measurements have the same center to them, but for some reason, because of small variations in where you put the block of metal down on the weighing pan, some of the observations have bigger standard deviations than other ones. And that heterogeneity, allowing for that heterogeneity in this way, will fatten out the tails in exactly the right way for the T distribution to appear to be the right thing. So it turns out that the right mixing distribution is a gamma. Actually, it's an inverse gamma. So it's a fact from basic distribution theory that Bayesians are interested in more than frequentists, that the way you can get a draw from a T-curve is like it says there in equation 22. First, if you assume you know what nu is, you make a lambda draw from the inverse gamma distribution with parameters nu over 2 and nu over 2. And then each person's actual y value, given mu and sigma squared and that lambda, is formed as a normal draw centered at mu and given by a particular form in which everybody's allowed to have their own variance. Namely, you take the common variance for everyone and you multiply it by that number lambda that is unique to each individual person. So that's a cool way to create a distribution with heavier tails than the normal by allowing everybody to have their own variance. They all have the same mean, but they're allowed to have their own variance. And the own variances are given by a combination of taking the common variance to everybody and multiplying by a number that's allowed to be bigger or smaller than 1. So another way to write down the T model that is a natural way to try to learn from it hierarchically is equation 23 there. You put a prior on nu, and I haven't said how to do that yet. And you might as well put one of the conjugate priors on sigma squared, scaled inverse chi-square. Then you put a conditional normal prior on mu. That's the conjugate prior for mu and sigma squared in the Gaussian model. Then you put this prior on lambda. That they're like IID draws from that inverse gamma with the nu that you got from the prior. And then finally, you make independent draws from the normal where everybody has their own scale factor lambda I. So pretty cool. And what we've just done is we've, in passing from the Gaussian model to the T model for the NB10 data, you remember from what you learned about the T-curve back in any previous probability classes that you can get as close as you want to the Gaussian in the T family just by making the degrees of freedom get bigger and bigger. The Gaussians turns out to be a special case of the T when the degrees of freedom are really big. And so what we're about to do in passing from the Gaussian model, which does not fit the data at all well, toward the T model, which we hope will fit better, is we're doing a standard thing that Bayesians call model expansion. You expand the Gaussian model in directions in which it looks like that model's inadequate by embedding it in a richer model class of which it's a special case. And then you try to fit the richer model and see if that does better. So this is an example of Bayesian model expansion, and we'll see how it goes. And this is a standard way to deal with uncertainty in the modeling process, like it says at the top of this page. When you find deficiencies of whatever model is your current one and you're trying to find a better one, a good idea is to embed the current model in a richer class with the model expansion in directions that are suggested by the deficiencies. And we'll see a number of examples of this as we go forward. So here's the Gibbs sampling data set I was trying to create on the page over here. You can see it a little more clearly right here. If you were to work out the single scan Gibbs sampler here, iteration 0 would start the parameters out at mu 0, sigma 0 squared, and nu 0. Iteration 1, you make a draw from the full conditional for mu 1 given the data and the previous values of sigma squared and nu, which correspond to looking back into the previous row. Then when you get to sigma squared, you get to use the latest value of mu and the older value of nu. And then finally, when you get to nu, you use the latest value of both mu and sigma squared, and you keep going. After you've decided that you're in equilibrium, you take rows 0 through b in this data set and throw them away. And then you choose a number little m that says how long you want to monitor, and you monitor throughout that period, and then apply standard descriptive summaries to the columns in the mu and the rows, the elements in the mu and sigma squared and nu columns to learn about the posterior distribution. So there you go. That's Gibbs sampling. To do it, though, if you were going to write your own R code to do it, you'd have to be able to work out the mathematical form of each of those full conditionals. And that's where the real pain is in implementing MCMC. If you're going to try to write a Gibbs sampler, you have to be able to work out the full conditionals, and they're no fun to do. And I've already mentioned that there are some other practical issues we have to face. So there's one of them. How do you figure out the full conditionals? 2, where should you start? 3, how large should the burn-in and the monitoring run be? 4, how do you know when the chain has reached equilibrium? 3 and 4 are MCMC diagnostics. Question 2, I'll just illustrate by example in case studies. And here's an example for full conditionals. This will show you why you yourself don't want to ever have to do this, because it can be done, but it's a pain. So let's think about that conjugate Gaussian model we looked at earlier. So the data are IID from the normal distribution with unknown mu and sigma squared. So the full conditional distribution for mu is just the the conditional distribution for mu given sigma squared and y. And here's the trick. To work out a full conditional, you're allowed to consider that as a function of mu for fixed sigma squared and y. And so here's how people figure out full conditionals. Well, by the definition of conditional probability, this is the top row of equation 25. The thing on the left that is the full conditional is equal to the ratio of the joint for all 3 divided by the joint for the 2 that you're conditioning on. That's just the definition of conditional probability. But look, the thing on the left-hand side is supposed to be a function of mu for fixed sigma squared and y. So the denominator in that first row is just a constant. I can just throw it away, put it into that thing called C. Now I want to try to expand out the joint distribution of all 3 things in a hierarchical way that matches how the data are modeled. And if you look back in equation 24, we should first start with the prior on sigma squared and multiply that by the conditional prior for mu given sigma squared, and multiply that by the conditional behavior of y if you knew what mu and sigma squared were. You just chain along to get the product rule for and, always conditioning on the stuff that you conditioned on that you assumed before. And so now multiplying that stuff out, I've got a prior distribution. Oh, now, first of all, let's look at this a little bit more. This is supposed to be only a function of mu for fixed everything else. And the prior then, p of sigma squared for sigma squared is just a constant in mu. So it gets absorbed into the normalizing constant again. And the normal prior for mu is written down there. You can see it, times the product of all those normal marginal distributions for the y's. And now I want to think of that as a function of mu for fixed y and sigma squared. And it turns out that you can rewrite it by expanding out the squares and collecting powers of mu and completing the square. And you find right away that the full conditional for mu is normal. And the updating rules, we've actually seen them before when we talked about the Gaussian before. Weighted average of the prior mean and the data mean, weighted by the prior sample size and the data sample size, and so on. So the full conditional for mu is a particular normal distribution. And now you apply exactly the same logic to get the full conditional for sigma squared. It's equal to the joint of all 3 over the joint of the things you're conditioning on. The denominator is again a constant in sigma squared. Now you factor just as before. And now it turns out that you need to bring in all 3 of those things because all 3 of those terms involve sigma squared. So you have the prior for mu, the conditional prior for mu, the prior for sigma squared, the conditional prior for mu, and then the final, the sampling distribution. And there's a whole bunch of noise here now where you expand everything all out and simplify, and out comes another member of the scaled inverse chi-square family. So after a lot of algebra and headache, we find that the full conditional for mu is a normal, and the full conditional for sigma squared is a member of the scaled inverse chi-square family. But would you agree with me, please, that you wouldn't want to do that every time you wanted to try to write a sampler? That's just nasty business, right? So in conjugate situations, the full conditionals have conjugate forms, which are tedious but straightforward to compute. And hey, what? We live in an age where we have a machine that is very good at doing things that are tedious but straightforward. Namely, let's turn this task over to computers. And so the people who wrote the WinBugs code have actually written a program that figures out what the full conditionals are for you automatically without you having to do it. And there are 3 such general purpose programs that do this right now. at least 3. The one I'm going to show you today is WinBugs. Then next time I'll show you how JAGS works for those of you who are Mac users. Also, JAGS runs under Linux as well if you're a Linux person. And then there's this program MLWin that I mentioned before that I was involved in the Bayesian capabilities in. WinBugs and JAGS are freeware, and MLWin has a nominal charge. They plow all the money from the charges for it into the development of better, newer releases of MLWin. So MLWin is a good package to know about if you find yourself needing to try to do MCMC on larger data sets than you would have tried to use on WinBugs. WinBugs will fall over if you give it a data set with 100,000 observations and 5 or 10 parameters. It's not well suited to trying to work with data sets that are even that small by Silicon Valley standards. MLWin does a better job of that. It was built in such a way that we can handle much bigger data sets. But it has a more restricted set of models that it knows how to fit. So you gain something and you lose something. So let's take our next break. When we come back, we'll actually start doing some WinBugs calculations. So video, guys, if you want, you can turn the video off now. And we'll start again at 2:45.